Much at some point, guys, because I was talking in the last video. I didn't finish that video, but I've lost track anyway. So the title is Active Directional Modeling for Fault Tolerant Safety Critical Systems with Tri-DAG Partial Consensus via Dynamic Scale via and Bioinformatics a model for for safety critical systems within the derivative system. A lot of words there. Let's break it down. Active dimensional model. This system data, it knows what it's doing. It's active. It looks at dimension. It knows what it's doing. Fail-safe mode. It's like a fault tolerance mode. Active modeling of computer systems. This is not to fix itself. This is not to act itself. It knows what it's doing. Fault tolerance can heal itself. Can fix itself. Recover an artifact that you lost or it lost. Safety critical. Real world danger systems. Tri-DAG apartheid consensus. Yes, yes, yes protocol. I say yes, you say yes, we agree. I say yes again. You say yes again, we do. We action it, and I say yes again. You say yes again, and then we then fix the problem. We try to find a way to do something. We disconnect. Or can I do something else? Most importantly, living forever and transcending. So polarity. Basically, this video is gonna be more formal, because it's more formal of the of the translation. I'm trying to send my PhD, which I'm gonna break through. But basically, my signal equals your noise. My noise equals your signal. That's not that's just polarity clauses anyway. So you get this here. So you get this thing called if you look at it very well, it's like an axis. No one should ever change this model unless want to kill themselves in our dimension. But this was called a sparse matrix. So basically, it's basically like this kind of matrix, but it's like a business axis model. So with the X, Y, Z, but you can see X, Y, Z. So you can get dash epsilon to epsilon in our X, and then that'll be the negative epsilon. Because if this is our X here, no, this is our X. Epsilon is the one. This is very important to understand. So you have two public keys minimum to talk to the world. Just to talk to the dimensions you are. But you have to have four public keys to basically it's like a half row. So half row is like my whole units, 4 units of security. It's just their half C units, their login units. So so their login is my one. So I can just say, oh, this I'm just login to store securely in their reference, and I say, oh yes, login in yes, login in your world. No. This takes one in my world. It takes half the time. So this is already broken. See for the space-time algorithm. Hypothesis. So basically, something I call the Hamiltonian invariant solution. So Hamiltonian, basically you have like a 6 type of graph, 6 type minimal. Based on the relationship, but you get a total of 9, 12 to do via phenomenal modeling. For example, you can have an E state go to and fro. Epsilon state, a nil state. You can represent a nil in your world and their world using an encoding table. The nil just means like a party nil. But if they this is me a nil, that'll be a minus epsilon state. But I'll receive their nil as epsilon. But if I send them a nil, once I send this back, I can never make it what. I have to flip it. You have to give them the same thing they sent me, the nil state, but in the minus epsilon form. When I send this is a duplex string model. So when I send this, I get the epsilon state. But this is not a good system, because when they get the epsilon state now, they can get this message and they can get basically I send them the epsilon, I send them the inverse whatever I have in my system. Basically, if they give minus epsilon, they have to convert it into what something they can understand, and that'll be epsilon. But that'll be epsilon in our world. But when we send it back, we get what minus epsilon. Basically minus epsilon in our world equals their epsilon. So when I send minus epsilon, they're receiving epsilon. So the problem with this is when I say yes to their epsilon, say I want to receive download some artifacts, I consent to it. Yes, I say them yes. And there's a mistake here. So if I say yes to epsilon, and then they send they make a mistake. Basically, we can make mistakes everywhere. But if they give me an epsilon and they say yes, this is fine, I get epsilon, and then epsilon is just nil state in their world. In our world, the epsilon state is just the first thing I say, which is not the minus epsilon. So the epsilon is not the minus epsilon. So the minus epsilon isn't same minus epsilon the same in epsilon. Yes, I cannot interpret what the epsilon minus epsilon means. That's nothing. That's nil in our world. That would just start degrading our computer. So that would be like the first proof. So basically, if they send me the first epsilon negated, just not do nothing. They send me no state, no solution, no memory. I'm meant to get it as epsilon naturally, because that's just the medium of communication. But as a mapping of encoding. But if they then send me an epsilon in the second instant, then nil, that epsilon is not. If it's send them this formal information in bidirectional input, I will send them epsilon, yes, and then I get minus epsilon. So minus epsilon is that. So when I do that, I get that. So you get minus epsilon, epsilon. So my encoding table becomes fragmented and broken. So I can never relay something coherent in that message channel unless I reset the medium. The medium has to throw out entropy and thermodynamics principle. So next thing, thermodynamics. Why? So this is consent. So at stage 1, the first trial is basically you have 3 trials. The first trial is the trial is agreement. We agree on the established medium to communicate. The second trial is consent. Are we allowed to do this? Are we allowed to? Do we agree on this protocol to talk to? And the third trial is just the negotiation. So yes. So basically, the how to fix this. I give this me 3 minus epsilon. 3 neo states. I know now the neo states. What the universe. It's called a triplet model. So the neo states is very important to understand. Very important because null is nil. So the neo state just means what is nothing to you in your universe. Which is nothing. We don't get any mistakes there. So we can send them our nil encoded. Just like so our nil will be epsilon. But we have to let them determine whatever that sparse structure means. So if I send them an epsilon, when to do this, I send up 1 epsilon. I say, okay, this stuff represents basically this medium has this properties. This means these properties. These properties are canonical to nothing in our universe. That means nothing of something, nothing of something. So nothing of everything. That's what that means. So that's nothing of everything. So basically, you get something. You get something of everything, and that means nothing. Something of everything, and something represents nothing. Nothing, nil, null, no memory, and no type. No. So the something represents something of nothing. So that's what you're gonna find. So the properties can be the thing in the like radio waves. Radio waves have the epsilon state. So if I have like a epsilon, that means there's no noise and no signal. And that's my medium of communication. If you have to make a noise in a signal, you have to create your wave, and then that will be what they have to relay back to us to say based on the consent, the first consent, which is like and then basically if they say with a nil and they get this, if the pulse is checking a nil, nil, you have to go to the other one, which is the other one. This is the protocol. How is your protocol structured? The protocol. So the first one is the trial. First trial is the agreement of medium channel. If you call the medium a channel, it's very fine. And then the third one is the protocol, and the third one is what the agreement of the system to grow, evolve, and via the channel model and the messaging packet, message paradox, whatever you call a message in your universe. So now I'll try to do this now. So this is fine for now. My signal is always your noise. That's the worst case. My signal, your noise. Your noise is my signal. My noise, your signal. Whatever the worst is. This is the try worst case. You got to try part of the worst case. So before I go, this is just the principle of consensus. Consensus means yes. I say yes 3 times. I don't say yes. A my own time, of course. In my own time, whatever that means. Because time is of the essence too. So red to black animation, done that. But what's the standard thing I'm doing for this? Yes, the dimensional light detector. I think I have to try to do that now. This might basically the sparse matrix has to have a basically, the sparse model of a state transition has to have the three-axis model for unit, fraction, and actually, the policy now. So, guys, don't make me ask again. Just do your job properly, guys. If you're gonna work there and work on things that can affect the whole universe. Yep. But last thing. So this I'm saying to you guys, it's not that it's a bad thing. So for me, if I want to ensure this algorithm has all the maximum integrity for security, I have to do it properly, and by properly, correct, I mean you don't touch my work. So basically, this is what I'm saying. This is called an encoding table. It's this is sparse matrix. It's just like a two matrix. You can have two matrices representing the same thing, polar systems. But this is all the matrices that race to it. This is what I've computed. It's a picture of it, Namdi. 3, 2, 1, minus 1, minus 2. So basically, basically, you have a parallel universe that's down. Let's say down, down, up. Basically, in all directions. In all polarity. There's a universe that's relative, and this is what the encoding matrix drew. Just by just like geometry, just in the local space of what we are. This is all the encoding tables to it. Okay. So basically, you have what state? You have the first state, the first axis. So the no signal axis is just only plus only signal just mean no signal and no noise. That's no signal. Now, then you go to no signal on the far right, 360 degrees. But 360 you come back, so you get basically for my point of reference, this is right. But in this quadrant, basically you get to go 90 degrees, 270 degrees quadrant. So you have to go 180 degrees to get no signal and no noise. This is the chemical state of the system. So you get plus epsilon equals to minus epsilon. And you get you get minus plus epsilon. You get 1 epsilon, 1 plus, and you get 1 minus plus epsilon equals vice versa. And now we can say we got positive. So if you flip on the x-axis, you're flipping the dimension. You don't really notice. That's the lattice you're flipping. So you can really just do it one way. You can do half rule. The half rule, which is very important. You do it understand this one. So if I'm going to one dimension, so basically the half rule is a policy now. So if I half of something, I get half of something. I go up, half of something I go down a dimension. So if I want to be in the sixth dimension, half of it is basically I'll do the inverse if I want to be in the sixth dimension. Because no theory anymore. So if I want to be in the sixth dimension, 6 times 2 is what? No, 3 times 2 is 4. Now 4 times 2 8. So I need to have 8-dimensional access to the sixth dimension to project myself to the sixth dimension. Because 3 times 2 is 6. Because so I have to get 8 dimensions to do this. So the security gates are there, so I can't see everything from my dimension up there. If I ever pop up to that reality, as a 2D being, 2D being. So how would I do this with this matrix, sixth dimensional being, Nandi? So for me, I have to make myself hurt. Not even hurt. The thing is, if I can go to 4D dimension, it's very easy to go to 2 dimension. So basically thermodynamic operator apply here, except the third one. Now the last thermodynamic operator doesn't apply in any way, shape, or form. It's relative. There's no relativity here in the bubble universe. So the first principle of thermodynamics, I believe, entropy is entropy or noise spreads towards disorder. Because basically the system is more stable as chaos than noise. Because if chaos is uniform, more uniform, more easy to structure, then that system goes towards it. It's not about the money. Basically, if a system can have all signal and no noise, and that's the uniform thing, everything is represented by nice little packages of 1 and 0. It's perfect. System doesn't have to worry about it. It keeps it uniform. It's a perfect world for everyone because there's no disease, no nothing. That kind of world, a utopian world you really live in, without even knowing to utopia. You know what I'm saying? So that's what I'm saying. That kind of interpret, but the universe is not perfect, especially the bubble ones, because they're worked on pi, prime framework. So again, pi is 2 pi r, 2 times pi times r, and that's the times the longitude. So the longitude is just the x dimension, the latitude is just the y. Now you get to another dimension, the polar dimension 2x. So to polarize this, I have to do 90 degrees. So 290, so 290 rotations, 2 half rotations. So if I do half of x what is that? Basically, if I do try to polarize x dimension and go up 90 degrees, I do 90 times x, 90x. That will go, basically 90x to be 1y. But you know, I have to polarize 3 times. So you need to be 3. So if I polarize y, x once, x times x, 2x equals 1y. Because you know, then 4x is what we'll polarize basically if 2y's is then 2y's equals 1z, so that'll be 4x equals 1z. So this is the half rule in partial, because you know half of y equals 1z. I'm saying to you guys, so that'll be the same thing, but if I want to go to the y axis, I have to do it double. So that's why it's have a dimension scale. So we got 1, 2, 3, 4, 5, 6. But this 1, 2, 3, 4 is a 1 half y. 1 half x equals y. But you know, you get 2 more bits, so the 2y has to come somewhere. So you get 4y, 1, 2, so you get 2 more quotables. So I'm trying to do it now. So you need one more 2y's, and 2y's is what? 2y's is 4x. So basically, I'm trying to give you the how I do this solution again. 2y equals 4x. So that's 4x equals 2y. This is a half rule in motion, half rule. So 2y, and then we get the z, and the z is what? 2y equals 1x, 4x, and then we have the opposites, and that'll be minus 2y equals minus 4x. That's just a conjugate pair of that, and then we have that's x, x. So you get the y. The y will be 1y will be 1 half, 1 half. Oh wait, no. 1, 2, 1, 2. No, that's not correct. That's not correct, guys. Basically get 8y's, 8x, 8x equals 2y minus 2y. So that'll be 1 unit. 1 unit is y. So half y will be 4x. Half of y will be 4x. Therefore, half of y will be 4x. Half of y is half of x is half of y equals 4x. Half of y. Half of y. So basically, you have to use your true mode. So basically, if I have 1, 2, 3, 4 x, that's supposed to 1y. Y. If I have 1, 2, 3, if I have like a 2x, so if I have like 1, 2, 3, 4, 5, 6, 7, 8, that'll be 8x. X equals 2y. So 3 words will be what? 3 times x will be no, basically it would double because 2 1. No, it will be 12. 6 will be like 2 plus 3y. This is real model. 3y will be what? 12. 4. This is 8. 8 plus 3. 8 plus 4. 8, 9, 10, 11, 12. 12y. So I need 12x. 12x equals to 1, 3y. Because that's the minimum of the tri-DAG system. To model them heterogeneous homogeneous. This is like an encoding I have to preserve based on my dimension only that I can observe. Therefore, this has to double one more thing. So 12 times. So I need 12 axis of 12 x-axis to 1y. So there 1y. Therefore, because you know 12 axis is what? You get 24 axis 24 x-axis. 24 x-axis 24 x-axis equals what? 24 x-axis equals sorry guys, 24 times 12 times 2 times 12. This is basically 24 minimum for healing, so topology. So I need 24 of their x equals to my 1y versus, and vice versa in the minimum invariant case. So this x can be the node. So if I have a task, and this was trying to model the Sparse model. So the goal of this is really for the critical systems. And how that works, guys, is you have this state. So you have a tripolar graph. So you have like a switch. You have like So you want to keep maintain 24 states, 12 states minimum, 12 minimum. So 12 but you have 12 states they can measure too. So you have 24 you can measure in your domain to make sure that it doesn't matter. So you have to do the integrity check. So if I have 12x, 12 like a 12x, 12x, and 12y, 12x and 12y, 12 not a slow process. I want to ensure this basically you have two 12x, and this is task can measure two 12 pairs of x. These are homogeneous data. So what I can do right now is 24 maximum I can observe, 24 dimensions I can observe to get that data. So basically, if I have one public key, two public keys, and measuring the x and the circle, and that will be the things I only measure to see my domain, in my realm, in my span space, where I currently am, that I know where I'm going with this. Therefore, therefore, you get two public keys, 0 and one key, and you get like a context switching. Now, this is very good. You can start code switching. Code switching is just like am I running this code or this code? It's like an elf interpreter. So that's one code switching is because obviously if I'm trying to, it's a universal translator, canonical translator, for the medium. So the troubleshoot should remain integrity over the state of sigma star, which is like the set of languages that are empty in the medium. For the chamber, the chamber is just like the radio wave. Am I going through radio wave? Am I going through whether I'm sending a channel, where the kind of sigma star and sigma duality is like sigma star just means because it's just a state machine theory, thermal theory, net force for everything that sends information that's incoherent. But the cognitive is very powerful for this. Because the sparse measure can resolve it quickly, especially with a quantum computer. Quantum computer really just because quantum computer actually measure reality, real world reality, and compute them in real time without actually looking. Basically, by looking at the quantum, you get the opposite of what the quantum is, and that's his resolve the state. So we get this one here, and you get this one here. So basically, the consensus thing here is living this thing here, this that I've said here. It's actually the consensus I'm worried about, guys. You guys don't mess this up ever in your life. Which I'll show you how it works now. So basically, I'm saying to you guys. So basically, how this works. So in my dimension, I have how many things I can measure. There's 12 things. The half rule fun I go up and down. But there's 3 dimensions. 3 plus 3 plus 3 equals 6 3 dimensions I can measure. A measure can observe. 3 dimensions I cannot observe. And 3 dimensions I may be to I can observe, but I cannot act in any way, shape, or form. So you have to try to resolve this problem with the KKK principle. So K for kinematics, so inverse K kinematics. So it's a kind of a shuffle of the systems. So I have a dimension I can interact with it. That's what I want to control. But how can I stop this from going to other systems? I can control 3 dimensions X, Y, Z, based on whatever propagates here, and then plus another 3 more D because things that I cannot control. That's all my boundaries of control, and then have plus 3 things I don't know. This is things I know. I know I don't know. Don't know or may never know. But I can control them. Maybe because it's about lensing products. So 3 plus 3 plus 3 is 3 plus 3 plus 3 is 9. 9 dimensions minimum. Containing all the informations I can access for that medium. And then you got a 3 plus 3 plus 3 times 3 times 3 is 27. So I'm gonna access layer 27 dimensions. 9 plus 27, and then you go one more. So you got like the medium, the canonical medium model here, and you got this is minimum locality of functions, and the maximum locality is here. Now we get nothing that means nothing. It's just canonical representation. You got 3 plus 3. Basically, you got like 3 times. Basically, you got you just add them up. So 27 plus 9. 27 plus 9. So 27 plus 9 is 57. We share 57 dimensions that we can all access, but no one have all the full information knowledge. So how this works there? So we get we're gonna use the table properly. So we're gonna create a table 3 ik 3 ik 3 ik 3 ik. No. So basically 3 ik 3k 3 nil. 3 plus 3 3 nil. A nil for us for all of us, and then you got the other one 3 ik 3 k and 3 nil. And then we need a 3 ik 3 k and 3 nil, and you get 3 dimensions there. It's like a vector model. So 3 plus 3 plus 3 is 9 dimensions of ambiguity forever. So but it's not the four globes. So we're gonna have to get all the dimensions. So the IK dimensions are 3 plus 3 on the first layer. Basically the K layer, basically the ratio, to give me a ratio to it. So 3 dimensions for IK testing plus 3 equals 6, and then 3 plus 3 again equals 6 again, and then this is the 3 plus 3 equals 12, 6 again. So we get 6, 12, 18 dimensions of things we can never control. Control that we use. They could be medium radio waves for the structure, and that's a shared, that's a sparse short. So our goal now is to shuffle try to do this properly. So say someone's go to sleep. This is a team model, but say there's 2 people, 3 people now in our group. We have to like someone like basically say me, I'm like say my friend, basically my friend is a lattice, a sphere, and I'm like a cube, and like a sphere, lattice sphere. Basically, me and my friends are 3D spheres in this model, but we just 3D because we have a bubble up, and then we can go up there. So there's one guy I need, Ryan. So my friend Ryan, and then we have one more Thomas. Thomas is an like someone as Jimmy. We got Jimmy here. Now Jimmy here. I don't care about Jimmy. So we get 3 states. So we got some kind of series encoding. So we're gonna do this properly. So we're gonna do this. So 3D plus 3D plus 3D equals 60, 90. 9 dimensions total we can act on. So what we can do properly is it 3 times 3, 1, 2, 3, 4, 5, 6, 7. Oh no, it's 7 dimensions, sorry. No, I'm not doing right. So 3 IK, no, wait, 3K dimensions. 1, 2, 3. Oh, no. Oh, sorry, it's just 6 dimensions. So we got 6 dimensions, and we can measure. 3 plus 3 is 3. We got 9 dimensions total we can measure, and not know anything of it. Never pull something out of it. We just observe it basically. 9 dimensions we can observe brushes. They get half of that, half rule. 9 divided by 2 is 4.5 dimensions they share with us, and the other dimension is times so we have something you can times 2. So if I want to go back, I have to get 4.5 times 2 is 9. We share a total of 9 dimensions. So 4.5 dimensions. I can see properly. I can access and measure and act on it. Hence the house rule. Actual. So what do I do with this? So 4.5 of 9 dimensions. How can I get information there? So key to this. So we gotta have me. Basically, I have a minimum of that means a minimum of some kind of topology set. Must model this as dimensions. So 4.5 dimensions. What does that actually mean, guys? So I get 4.5 dimensions for anything. So if I'm basically my friend Ryan, he's a bubble. We're just bubbles. In our world, we're just flexible. I'm a circle. I'm a sphere. He's a plasmoid. A plasmoid bubble. That's a 4D bubble. Basically, we just built bubbles in our universe. And me and Ryan have a consensus. We get one more guy. His name is Richard. It's called James. Now James or Jimmy, whatever it's called, James is a triangle. Now triangles don't fit in a universe, so well, so I don't like this model anyway. I mean, so basically, Jimmy comes here. He's not in university. He's rigid. He's neurotypical. But one day he's working on a project, and then the project he gets stressed. He gets stressed, and he says, "Okay, I'm gonna go rest." Or so basically, someone makes him go to rest. And Jimmy goes to rest. So now Jimmy has one private key. One private key has to hand out to someone, but he can't hand it to me because I get crazy or Ryan. So we have to get the key properly. So the same model but sparse model. So I can say to Ryan. So Ryan says to me, "I want the key. I want the key. I want the key." And I say, because you had last, I don't trust you. And then and then we just pick a random shuffle. So I say, I'm Sicko, yes. I'm a Sicko, yes. Yes, you want a key? Keep the. I don't want a key. So I don't want a key. We agree. So we play a game of shuffling. But shuffle has to be equal to the space-time continuous 4.5 dimensions model. Where so basically, I'm computing over dimension axis. So I have to compute each dimension. That's 4.5 of the variance storage. So we have to define an algorithm that shuffles it over heterogeneous space. Homogeneous is basically the first dimension is really the tripartite. So after just write, so basically a shuffle is just a random seed that you generate. So that's what shuffle is in this context. You see it if I write with randomness noise, but it's not. So basically, so now basically if I want the responsive of x, which Ryan does want, Ryan goes first. So Ryan's first shuffle input is what I wanted. So Ryan and Namdi are tables. So random gets the keys in the sequence of every time I don't care, Ryan gets the keys. So Ryan gets the key X. I get O. Ryan gets what? O. I get X. Ryan gets X. I get O. Ryan gets X. I get X. Ryan gets X. I get O. Ryan gets O. I get X. Basically Ryan gets O. I get X. Ryan gets X. I get O. Ryan gets okay. But basically you have to try to exhaust this principle there. But the same thing applies for half. Basically, if I'm excluding for the half dimension, I'm already fucked up. So I have to do 9 dimensions. Basically, if I have the problem, that means there's something else they don't know. It's space and commuter. This is security. So if I have half dimension, which is 4.5 dimensions, I target. Their algorithm have to break this with a 2-to-1 rule. So that means the space to time auxiliary control is not good enough. So if they get 2, if they give me a 2, that's a 1 units in my world. 2 key, and now or if they have 2 space to store something, that 2 space to store something is my 1. If they can compute it over time, the time is 2 times. If they can do the roll 2 times, that means that because the space of my 1 unit is nothing, and my system is broke, and that doesn't really matter in my world, and there's a space-time glitch. That's what it means here. That's what I'm trying to give you guys. So the system has to remain the 9 dimensions. But 9 plus 9 is what 18 dimensions. So in the worst case, and in the best case, if this algorithm works, this worst case 9 dimensions of failsafe, and then we get 9 plus 9 minimum dimension. 9 plus 9 plus 9 is 27 dimensions of access to ensure that I don't bridge my reality. Didn't bridge my reality without consensus in the loop. That's what I'm saying to you guys. So thank you guys for watching this video. Hope you have a lovely day. I'm gonna continue next video on Hamiltonian and the graphical function. But the third law of friction is not real. Because there's no the third law of thermal is not real. So you got thermodynamic principles here. So basically, I'm going to explain to you guys before I go. So the third law of friction doesn't apply here. It doesn't slow down. No system slows down indefinitely. It's all about evolution. The first principle, Hamiltonian resolution. So you get here. So basically, my half trip. Since like a graph. So basically, this is like basically the dash, the space in between is basically space. Basically, the arc is like the space model. So I can go arc space the arc, really just space it. So if I have like there my epsilon or my 0 is there 180 degrees, and vice versa via the model here 0 180 0 80, and then the 0 epsilon is epsilon, and then there's 0. Basically, my 0 is their 0, and their 0 is my 1. So basically, if I'm putting a 0 here, I'm saying this is 0 and epsilon. This epsilon is just means the 1 to them. 1 unit. So basically, 180, basically A to B model. So if I'm with, if they come from my position, code B, and I'm saying their B is my A. This is what I mean. So if the all this picture, it's just a 2G away journey. But you want to get there half the time. So if A starts equals B end, A starts is B end. Basically, if A X and Y is and you flip that, you pluralize AX equals 1Y, AX equals 1Y, but they have to take the time to go there. So AX is just a journey, but that journey is not linear. It's not linear, so they have to go in a curve. Because they're not doing the math properly. So what they have to do is probably just to try to get to just right angle to what B. But my B is their A. So for referential, I'm correct. So for their A to come here in my universe, they have to go through 180 degrees turn, and that's a waste of energy and resources over the chamber model. So what you have to do is AXY for the dimension AXYZ for the coordinate system I'm in, and then we get let's say A. So it's like basically you get two little A's to do it. So little A1 is A is Z, A dot X is the Y dot G, and this is my 180 degree frame of reference to us. And but that's just to move 180 degrees on the X axis alone to the property. But that's X axis. You have to go through a line. Line segment to some array. The y-axis is just like a grid. You have to go through some kind of linear lattice portal. Just walk it to the lattice, and then z is for some kind of geometric structure that protects the whole system to do it XYZ units. So that's what I'm saying to you guys. So if they try to go, if they go half the row, that's my unit. If they go half the unit, that's mean they go basically. If they try to get here and they get half, that means they have 1 unit already. As well. So literally, when they go 2, they get no. So if they try to go half, half is not 1 unit. So if they try to go half, they're going a third, a quarter in my view, in my frame of reference. Because a quarter is like a unit calculate user between here. So if I get a half of the system, if they go half in my worldview, they're going a half is a quarter my one view. I'm into seeing a half, a quarter, a quarter. But then they have view. If they actually do go half of view, that means they're going. If they actually do go, it just basically it's half and half. So if they go half, I'm seeing a quarter they want because that's the journey. So but they have to go twice the journey. So a half times a half is 1. 1 times half times 2. So this is 2. 2 halves equals 1, and then you get a quarter. So the goal of this is to model the homogeneous space-time coordinate system for log n competition. For example, the lines are the sparse matrices going through, but it's like a dial system. So you have to ensure that you're not wasting time with this dial model, because this dial model will actually blow the bubble, because there's not enough space to compute the time based on auxiliary computation. But you already know something is there. You just can't align with it. So that's the problem that's there for the invariant one. So if you understand this problem, you have it for the first law. But the first law of thermodynamics says that. Now, second law is what? So the second law of thermodynamics. So the first law was something about conservativity. Force equals net force equals 0, and that's like a chemical state. And then the second state is force equals mass concentration. So if I go 2 halves, I get 1 journey. 2 halves equals 1 journey. 1 half equals 1 half equals 1 journey. A quarter equals half of a journey. But the goal is to have the maximum journey transcend the system. So you can go anywhere in halves or quarters. The canonical model for the system is just a quarter for the 2 keys. So if I have 2 keys, A and B, and they store a half, that's perfectly fine, because you don't even need to store everything. So it can store 2 halves of 2 halves. You can store 1 half a homogeneous zeta, things like understand that it can structure, and other half heterogeneous model. So you get like two functions that store 2 functions that map to 2 inputs. That's like 1 whole. But that one hole is not fully a hole in the sense you can use it, because it's not bound to the system yet. That's just there. So when you have this one, you have to have the other one, which is the other one means like you get the other one's half of a half, half plus a half equals a quarter. A quarter. So you get a quarter. Now that one quarter in their view is one whole. One quarter in their view is half. It's half of some information. And in your worldview, that one quarter, one half, one quarter. Basically, you have two public keys. There, your one quarter. Basically, yeah, we'll have one half plus one half equals one quarter, and that's two public keys. And then that public keys is one half, two one half. So they basically, if they actually do bring a public key, you get two halves, one quarter, and they're able to make sense of it because you get one quarter, one quarter. But you have to have the rest keys stored too. So you have to have the rest quarter. That will be times three. One half Helmo, genius data, and one half heterogeneous. That will be basically one half times 4 is 4 over 1. 4 times 4 is 16. Number 16 over 1 over 16 states. Classes some of you can do quickly. But 16 states is just public key bound. And then you get the other half. So that public key has to be sparse too. So you get 14 times 2. One half is like one half times 2 is 1. 1 basically 14, one half squared is a half. So you get 16 and a half. 14 and a half minimum. 14 and a half minimum. 4 8 2 28 dimensions access. So you never want to let it be 29, because you basically have to get one less dimension, and you have to supply something you can't see. Just negate the whole thing from the column model, because the Hamiltonian graph cycle is very important to understand. But the thing is, you have to understand that they work on principles of weights, the weights, the time space time weight, based on the segment tree model. So you get a self-balancing segment tree. You can use a red black elimination, which just means this is noise, this is data. This data is what I need. So you get the algorithms you use there, which I'm giving you now by just telling you this. Red black elimination, red to black elimination, which just means the red nodes are pruned. Things that become dangerous are pruned from the system, and the black just means that it's sustainable and we'll keep it and we'll leave it forever. It can be noise, but you just have to stay there because it's kind of cool information. You get pruning, priority pruning. So you get like the priority elimination, but the priority pruning. So if I have like encoding state 0 0, but it actually means epsilon. I don't need it to just prune the 0 0 and just discard the information. So I priority prune. So priority just to if x is 0, then we prune x up y. Something else. If basically you got something called an if then else policy. If x happens if x is y. Basically it's like for the lattice model. So if the union of x and y is disjoint, disjoint just means that it's not needed. The x and y you get y, you get the invariant x y y x x y. So if they just get together intersection will be just a noise, and now epsilon. But they then loop, they then close like if this is true, then perform this operation. You can go like this is like close to all the functions. So you get in Gaussian. So the Gaussian so if then else if then else if then because the then clause for the systems is mandatory for the it's a policy in Gaussian programming language. But you only get basically that's one policy can go two ways. To give you the right consensus and no one get involved and watch you. And you have the other systems like while basically while system while x less than 3 do this but x has to be less than 3 union this sets between boundaries 3 to 100. Doesn't make any sense to me. So I said so my one doing is like when while x is less than 3 less than or equal to 3, you perform some arbitrary operation, which is like the polarization of the system. Then while when then do something then basically you don't want to even have like an issue with the error handling process. So what I'm saying to you guys, it's gonna be prone to errors, a lot of things. So while something's happening, then do something. But when something else happens, then when. So you get when when x is even, then do y. And then when y is even, when y is even, when I is even, do x. So basically, you got the two kind of loops. You got the when loop, when while loop. So we get basically you have like a bracket to it. So you get when this happens, while this is happening, uh, do this, observe only. Try to reduce the process. Basically, when you reduce the process, just observing the state and resolving automatically. Because you just have to like actively do it. Based on the system to do it. So you got like a signal system. So you got the system just has to resolve itself with a policy system. Because whenever a car going to Uber, doesn't really matter. It's just when x is zero, and their zero is my one. That's gonna be problematic. So I have to context switch between when there's zero, when we get zero, while we're still in direct straight, while the zero is while we haven't polarized to one, while we've not got a one, but this is like ensuring the system is coherent enough to be developed upon for the next day and the next day and for days to come. Okay, thank you guys. I'm OBINexus Nami signing out.